All right, you are now aware of this equation, which has to do with the force acting upon a charge that enters into a region of external magnetic field. The charge is going velocity v. All right, there is an alternative way to express this equation that instead of talking about the velocity of a charge, you talk about current. After all, current is charge moving through a conductor. The alternative way to express that equation is this, and I'll show you where this comes in, how the one on the right is derived from the one on the left. The basic idea is that you have a conductor. Let's say this is a piece of conducting wire here, and it's in an external magnetic field, and let's say the magnetic field is directed into the page here. So that's B, and we have a current that is going into the wire. This is a conventional current flow here. All right, and the wire, let's say it has a length of L. All right, the current that is flowing through it, you know that current is charge per time, and if we're talking about a nice, steady, continuous, uniform current, then it is just Q divided by T. If we talk about how long it takes a charge, individual charge, to go from one end of the wire to the other end of the wire, well, we're talking about the drift velocity in that case. And in that case, L is equal to V sub D times T, where V sub D is the drift velocity, and T is the amount of time it takes that charge to drift from the left to the right, go a distance L here. All right, well, if I solve for T out of that, T is just L divided by V sub D. Then this Q, which is I times T, can be written as I L over V sub D, like that. All right, now let's suppose that this wire in the magnetic field experiences a force, which we could write as F equals Q V cross B, according to the old-fashioned way that we've already done. And if we're interested in just the magnitude of the force, then that's Q, and the V that we're talking about could be V sub D, the drift velocity, times B times the sine of the angle between V and B. All right, now this Q, let's write it this way. So Q is I L over V sub D multiplied by V sub D times B times the sine of phi. You see the V sub D's will cancel in this case, and what we're left with is I L B times the sine of phi. Now, if we treat L as if it is a vector, and we call it, the magnitude of the vector is just the length. The direction of the vector L, we'll say, is in the direction of I. So if the conventional current flow is going to the right here, then that will be the direction of L. So L is this length here in that direction there. All right, if that's the case then, and we treat this like a vector, B is already a vector, I is not a vector, but it does have a sign associated with it, so it is a scalar quantity, then we can write this as I L cross B. And that's where this equation right here comes from. Okay, so we've got another form of the equation that we started with here. And this one specifically is used for currents in a wire. It's real simple then to determine the direction of a force based upon the right-hand rule if that wire has a current flowing through it and it's in an external field. So in this case right here, you use the right-hand rule. L points in the direction of I, so points that way. B is into the page, so my thumb is pointing upward. So there is a force acting upon the wire in that direction right there. Well, that's how you can compute the force for on a current-carrying wire. If I were to take this and I were to break it down into a differential form, let's say, then dF is equal to I, we're assuming a constant continuous current flow through the wire, which would be the case, times dl, and we're also assuming a constant continuous magnetic field here, then this becomes the differential form of the force. Now we can use this form here to solve some more complicated problems. Let's do that now. Let's say that we have a wire that is shaped like this. That's a circular portion there. And it's got these two flat portions on either side, and then there's this circular portion here. And the length of this side over here, we'll say, is L. Length of this side over here, we'll say, is L as well. And the length of this entire side here, we could consider that this way. Let's say this is the center of curvature here, and we have a radius here of r. Let's call it r prime. Then we could figure out that length if that's half of a circle. All right, now let's say for that conducting wire here we have a current, and the current is coming in this side, current I, and it's leaving this side. So through this circular portion here, the current is going in that direction right there. Now let's take this current carrying wire and let's put it in a magnetic field. And let's say the magnetic field lines are uniform, pointing directly out of the page here. So those are our magnetic field lines. They're pointing directly out of the page. Now, what we can do is we can figure out the grand total of all the forces acting upon this wire here. And in order to do that, we're going to use the equation that dF equals I dl cross B. And you can guess here, we're going to have to divide this up into sections. There's going to be a force that acts upon this section. There's going to be a force that acts upon this section over here as well. And then there's going to be a force that acts here for the center section. So let's call this section 1 over here. The middle we'll call section 2. And then this will be section 3 here. If we want to figure out the total force, F, then it's just going to be the force on section 1 plus the force on section 2 plus the force on section 3. But we've got to be careful here. These are not just numeric values, these are vectors, which means we have to consider all of the directions and all of the components required to do that summation there. Okay, for section 1, think about the direction for that one. Put your right hand in the direction of I, curl your fingers in the direction of B. This is B, recall. B is up out of the page, so I, if I turn it this way, I, that's L cross B is up, so there is a force in that direction right there for F1. The same would be true over here for area 3. I sub L cross B, forces downward in that direction. Okay, so turning it back around now, you can see this is force 1, this is force 3. Now we've still got force 2 to contend with here, and that force, because L is going to change here, for example over here the L vector points that way, but over here the L vector, which is always a tangent to our curve here, points that way. At the top L points that way, over here L points that way. So you can see the L vector, which is going to be a tangent, the dl vector I should say, is going to be a tangent to the curve at every point. So what direction does the force point? Okay, right here the force points towards that central region there. Up here the force points towards that. Up here the force points that way. So all the way around you can see the forces of all of these individual dl segments all around this curve here. All of the forces point towards the center. So all of these are df forces there. All right, so dealing with area 1 and dealing with area 3 is going to be straightforward. Dealing with area 2, we're going to have to do a little bit of math. Okay, so let's break this up and let's deal first of all with area 1. Well, for area 1, that's pretty straightforward. It's I, L cross B. All right, we know the direction from the right-hand rule, so we need to determine the magnitude of F1, and that's just I, L, B times the sine of the angle between L and B. Now, if you look here, L is in the plane of the paper, pointed in that direction. B is directly out of the plane that way. So the angle between L and B is 90 degrees, which makes the sine here 1. And our value, our numeric value, is just I, L, B. So if we had numeric values for I, L, and B, we could compute F1 here. It's just that. Now, F3 is going to be exactly the same. It's going to be I, L, B. So these two forces, when we add those together, they point in the same direction, so we will just numerically add those two things together. This is F1 plus F3 is just 2 ILB. And we do say that because they point in exactly the same direction. All right, so we need to deal with area 2 now. So here comes F2. Well, to do F2, we're going to have to break it up into sections, so we need to rely upon our DF is equal to I DL cross B. And now when we do that, let's sort of enlarge that circular region up there, here. If we pick a spot, say there's the center of curvature right there. If we pick some spot over here, let's say some DL section, that's a segment DL right there, then there's going to be a force DF that's pointed downward in that direction. So that's DF. Now we can define an angle here. So let's draw a dotted line here that represents the base. This angle here, we can call that angle theta. Now that angle theta is not the same as our phi that we've used up here. So this is just an angle that's going to go from 0 to pi, because we're going to have to integrate over this surface here, over this curve here. So DL is in that little section right there. So that's DL section that's creating this force DF. And if I break that force into components, I can break it into a component going that way and into a component going that way. Now, if you're doing the calculation here based upon this angle here, then this component here is the DF cosine theta component, and the component going down is the DF sine theta component. Now, we can use symmetry arguments here and say for any point that's at angle theta on the left portion of the curve, over here on the right portion of the curve, there's going to be an equal point. And that is going to have angle theta. You can break that force into components going that way and that way. And notice what happens here. The DF cosine components are going to cancel each other. However, the DF sine of theta components are going to add together. So what does that mean? That means that our DF for area 3 is really going to be the DF sine theta components that we need to concern ourselves with, and we don't need to concern ourselves with these horizontal components here then. Okay, so doing the calculation then, F2 is the sum of all of the DF sine theta components going from 0 to pi. And now we can plug in for DF. That's going to be the integral from 0 to pi of I dl times b times the sine of theta. Now again, this theta is this angle here. We deal with the sine of the angle between these two is going to be 1. So I didn't even write that here. If I were to write that, it would just be sine of phi, which we would turn into 1. Okay. All right. Now, here's what you need to realize. If we're integrating over dl, and since we're talking about a circular arc here, then L is equal to R times theta. So that is the length of this if we were to straighten it out. That's the arc length. This is S equals R theta. Theta is going to be in units of radians. R is that radius there, which we could call R prime. And L is the total length here. Okay, not necessarily the same as these total lengths here, although it wouldn't hurt if it was. All right, well, then dl is equal to r d theta. That's true because r, in our case here, is a constant value for all angles between 0 and pi, so we can say this is the differential of dl. And I can substitute that in right there. And when I do that, f2 becomes the integral from 0 to pi of I times r d theta times b times the sine of theta. Now, many of these things here are constants. We can factor those out. For example, I is a constant, r is a constant, b is a constant, and we're left with the integral from 0 to pi of sine of theta d theta, which is probably one that you can do. Now, when you do that, you're going to end up with 2IBR there. Now, that is F2. And what's the direction of F2? Well, based upon our symmetry arguments here, there is no horizontal component. All that we have are these vertical components pointing down, so the net direction in area 2 is also down. So F1 points down, F3 points down, now we know F2 also points down. So this vector summation becomes really simple then, that the total force is just algebraically F1 plus F2 plus F3. So it's going to be F1 ILB plus F2 2IBR plus F3 ILB, like that. Do that, and what do you end up with? Looks like we've got 2ILB plus 2IBR. And there's our answer. So that's the total force on this, and the direction is downward as drawn. As drawn where? Right there. Okay, so there we have our answer to what is the force on this current carrying wire system here. Okay, let's do another problem then. Something here. Let's say that we have a train track, and let's look at it from above. This is one rail of the train track, and over here, some distance away, is the other rail. Now, the distance between these two rails from there to there, let's say it's a nice equal 3 meters, and this is the top view of the rails here. And now let's say that these rails are in the magnetic field. Maybe these are train track rails and they're in the magnetic field of the Earth. So if the Earth has a magnetic field at this position, let's say that it is pointing downward directly into the Earth. That simplifies things for us. And this is our magnetic field B. Okay. Well, if we put a train on here, let's say that one of the axles of the train, the wheel looks like this when seen from above. There's the wheel, there's another wheel, and then we have an axle going across here. So this is one wheel there, this is the other wheel there, straddling the rails, and then this is the axle. And all of these are conductors. Now, a train would probably have more wheels and axles, but let's say that we're just interested in this one. Maybe this is the last one, or maybe the first one of the train, and everything else is non-conductor. I don't know. We're making stuff up here. Well, think about what's going to happen here if I do something like put a current through this rail. Let's say the current goes up this rail. When it gets to this wheel, it crosses through the axle and then can come back down in this direction. All right, if that's the case, then there's going to be forces, because now we have current carrying conductors in the presence of an external magnetic field, so there's going to be forces involved. Now, these rails we're going to assume are nailed down. They're not going to move. They're fixed to the earth very solidly. However, this wheel on top of the rail can roll and carry the train along with it. So if we look at the force that's acting here, let's make an assumption that the current is going upwards in that direction right there. That means the current is going through this way and then back down through that rail that way. So look, use your right-hand rule. What is the force on this rail right here? Well, it's going to be IL cross B. It's going to be in that direction. So there would be a force in that direction. And again, we're assuming that the rail is fixed in such a way that that force isn't going to move the rail, that it's nailed down. But nevertheless, there would be a force due to the current in that direction. And now if you looked on this side here, turn your hand, IL cross B, yep, there would be a force in this direction as well. So maybe we've got cross ties here connecting these two rails, and those cross ties are non-conductor, let's say. Then the force that way and the force that way are going to be equal to each other, so this thing doesn't move, if that's the case then. However, think about what's going to happen here with the axle and the wheels. IL cross B, there's going to be a force on this that is in that direction, there. Let's call that F1, this F2, and this F3. We know that F1 and F2, if these lengths are the same here, will be exactly the same in opposite directions, so those two forces will cancel each other. Nevertheless, there is this force right here which could carry along the axle, and if there's a train attached to it, carry along the train as well. Now, if we were to look at that, say, from a side view, so let's get a side view here. Here's the rail, and we're looking at it from the side. There's another rail on the opposite side into the paper. And now we've got the magnetic field lines, which we are assuming are straight down here, like that. And then the train wheel is, say, right here. The axle is right there. And if we're looking at it from this side right here, so here we are, let's draw a little eyeball here. That's us looking here. Of course, we're standing up, so the current is coming out of the wheel this way and going on this nearest rail in that direction. So we've got the current going this way and that way, so IL cross B, there would be a force in that direction, so that's F2, the same F2 that's over there. So that force could carry this wheel along the rails here. The question is, if we had some realistic numbers here, what is this? What is the current necessary to move, let's say, some mass along? Let's pick a mass of let's say 10 kilonewtons, and we'll say that's the force necessary to move this train along. All right. Now that would not be the mass of a train, so this would be like a small train. Okay. So 10 kilonewtons is the force necessary to move this thing. All right. Then we can figure out, we've got the direction of the current here. We just need the magnitude of the current. So based upon our assumptions here that everything is at right angles to each other, then F equals I L cross B reduces down to the magnitude of F is equal to I L B times the sine of the angle between L and B. Well, L is this distance here. We really don't need to concern ourselves with the rails, we just need to concern ourselves with the axle here. And the conducting path is from where the wheel on this side meets the rail to where the wheel on this side meets the rail, which is 3 meters between those two. So that's our L. Our L is going to be 3 meters. Our current's going to be I. B, well, we need a realistic value for B. Let's just pick something. Let's say B equals a nice round 10 microtesla. I'm just making up numbers here. So we know that our force needs to be this. We know that B is that. The sine of phi, that's the angle between L, which is 3 meters along that axis there. Over here in this, L is coming out of the page. And B, so B is downwards, so the angle is going to be 90 degrees, so this is going to be 1. So this reduces down to just I, L, B is equal to the magnitude of F, and we need to solve for I. I is F over LB. And if I plug in 10 kilonewtons, that's 10 times 10 to the third newtons, divided by L, which is 3 meters, times B, which is 10 times 10 to the negative 6 Tesla. And now we need to do a calculation. That turns out to be 3.3 times 10 to the 8 amps. Okay, so that's a significant amount of current. Let's see, if I make this number bigger, I can make that number smaller. So that's 3, that's 7, 6, 333 mega amps. A big amount of current. I mean, it's not impossible to generate that, but your lights are probably going to go down in at least a block or two if you use city power. So anyway, 333 megaamps is a lot. That's probably why this method doesn't work for moving trains along. Nevertheless, you get an idea here of what's going on, that it is possible to move things along a rail. If you could figure out a way to reduce the friction down, perhaps this reduces down significantly, or perhaps you can come up with a way to increase that significantly. If you increase that, then increasing the B makes the current smaller. Alternatively, decreasing F makes the current smaller as well. You could also do some changes with L here. You can increase L, and that would also make I smaller. Nevertheless, just playing with the terms here, it's going to reduce down. You can change the current somewhat, but the way that we've got the design set up here, it's just not going to work very nicely for us. Let's take a little side trip now and talk about another of Maxwell's equations. You've already seen Maxwell's equation, the one for Gauss's law. Specifically, this is called Gauss's law of electricity is the one that you already know. You know that the closed integral E dot dA is equal to Q enclosed over epsilon naught. And we've seen that if I have, let's say, a positive point charge here, the electric field lines go outwards in all directions in space, like that. And then if I have a Gaussian surface and I enclose that I enclose the charge in my Gaussian surface, then there is a flux through the Gaussian surface that is equal to the charge enclosed divided by epsilon naught. So what's on the left-hand portion here? This was the electric flux. Specifically, it had to do with the electric field lines that were passing through the Gaussian surface here. And it said that the electric field lines, the flux passing through the Gaussian surface is equal to Q enclosed over epsilon naught. Now, if I did something like this, if I had a dipole, then you know that if I have my Gaussian surface out here, my Gaussian surface is not enclosing a charge, then you know that there is a flux of 0. So flux for that case right there would be 0. If I did this as well, my Gaussian surface is now enclosing both the positive and negative charges. You know that the flux in that case is also 0. But if I have my Gaussian surface enclosing just one single charge, then in that case, the flux is not 0. All right? Hopefully that's review. You know that. We're going to take this same concept, though, and now we're going to apply it to magnetism. So we come up to another of Maxwell's equations, Gauss's law of magnetism. And it says this, that the closed integral B dot dA. Okay, what is that? That is also flux. Specifically now, this is magnetic flux. So we're talking about the flux of the magnetic field lines through a Gaussian surface and not electric field lines through a Gaussian surface. Well, what's that equal to? Well, I'm going to let you figure this out because up here it was equal to the amount of charge that was enclosed. So if there was no charge enclosed, and remember that's net charge enclosed, if there was no net charge enclosed, then the flux was 0. You saw it here. No charge enclosed, 0. In this case, the net charge enclosed is still 0, so you got just as much positive as negative, so the total flux is 0. And down here, only when I enclose a charge do I get a flux that's not 0. All right, now think in terms of magnetic field lines. Let's draw a bar magnet. Here's the North Pole, here's the South Pole. How do the magnetic field lines work? Well, they go like this. They come out of the North Pole, they terminate on the South Pole. So magnetic field lines are going to look something like that. And the direction is from north to south. There. Okay, that's true outside of the magnet. And we talked about how inside the magnet, those same field lines go from south to north. Okay, now let's do what we did up here. Let's take a Gaussian surface right there. Okay, what's the flux through that Gaussian surface? Well, you have just as many field lines going in as you do coming out. And what does that mean? That means the flux for that surface is going to be 0. All right, what about down here? Again, I have just as many field lines going in to the Gaussian surface as I do coming out and hitting the magnet. So that flux is 0. All right, well, can we do what we did up here? Can we enclose the equivalent of a charge for magnetism? Because when we enclosed a charge up here, we got a non-zero flux. What about if I enclose a pole? Okay, what about now? Well, again, this is a difference between electricity and magnetism. Look, the magnetic field lines that are coming into this Gaussian surface are equal to those coming out. Because the magnetic field lines inside the magnet go from south to north, if I try to enclose just that south right there, well, I am not creating a flux that is non-zero. I'm creating a flux that's 0. Again, because magnetic field lines going in equals the amount coming out. So again, flux equals 0. So can you think of any situation, any place where you could put a Gaussian surface and not have a 0 flux? And the answer is no. Because if you could come up with a Gaussian surface that only has magnetic field lines going in and none coming out, then what you have enclosed is a magnetic monopole, which we have said they don't exist, or at least we don't know if they exist. They haven't been discovered. So what does this mean? That means that what goes on the right-hand side of this equation is 0. So this Gauss's law of magnetism, one of the Maxwell's equations that we've talked about in class, says that the total flux for magnetic field lines is always going to be 0. That's another way of saying there are no magnetic monopoles, that everything in magnetism is a dipole. All right? Whereas for electricity, you can have monopoles. You can have independent positive and negative charges. Here you cannot have an independent north pole or independent south pole all by itself.